Today I'm going to be presenting about my graduation research titled Fast Environment Reputation Based on Metadata Analysis. My research supervisor is Professor Takeda. My presentation will follow this agenda. In my research, I am going to implement a system that can detect Android malware by analyzing metadata inside application files in order to classify and detect malicious one. A machine learning named on-cast support vector machine. In this research, I will focus on the goal of the research is to build a system to distinguish Android malware from benign applications, and the research is focused on a static ways to perform a source detection. I do the research in the context that over the last few years, there is an explosive growth in smartphones, and Android has become the most popular operating system for smartphones. Unfortunately, along with the growth of Android, the number of malware on Android is also increasing rapidly. The graph shows that the number of malware increased triple in quarter 2 2012. Security researchers spend a lot of time analyzing binary files to understand the malware behaviors. I am going to be describing some related works. The first one is detection of malicious application on Android OS. Malicious applications were those that can access capabilities to sensitive data and transmission capabilities as well. At the same time, deceiving the users by pretending to offer service typically does not require some capabilities to make a legitimate use of the methodology derived on the comparisons of the Android security permission for each application with a set of reference model. The second one is static analysis of executables collaborative malware detection on Android. In this research, the authors proposed a method which was based on the collaboration. Therefore, a set of entities were able to work on a common task without predefined roles. The collaborative schemes were used to interact with other devices in order to exchange detection data and system information. It could be considered as the operations mode when mobile devices were relying on the remote server. Each device would analyze ELF, and ELF had a executable files and exchange detection data and system information with device. On device would send the ELF analysis to labels when an event occurs, then receive the results. third one is exciting Android malware characterization and evolution based on the collected Android malware samples. This code performs a timeline analysis and then characterize them. From this list, some popular characteristics of Android malware started. They are Android malware repackaged as popular applications. Android malware includes platform level exploits plans to escalate their release, and Android malware subscribes to premium-based services with background SMS messages. Now I'm going to be presenting my approaches. The method is based on the analysis of metadata inside application files. I am using support vector machine for classifying applications and detect malicious ones. Metadata is data that gives information about data. In the case of Android application, metadata is the data that describes the application. And Android applications are typically packaged in APK files. This is zip files, and metadata from the files will be retrieved by decompression and disassembling into text form. In my research, I will focus on meta info folder in two files, Android manifest.xml and classic.txt. The metadata are considered to comprise many information about the application, such as access privilege, wrapper, libraries, request permission, API code, etc. In order to classify applications and detect the malicious, I will use on-class support vector machines. This is machinery used for low-quality detection, that is, given a set of samples, it will detect the boundary and classify reports as belong to the set or not. I will use Scikit-learn, a package for Python programming language. In order to implement the system, I am using Python. Besides, I use Android SDK to manipulate Android files. The system will use the Scikit-learn package as the implementation of support vector machine, and APK tune will be used as the disassembler. Basically, the system are divided into three modules: metadata collecting modules, metadata analysis module, and training and detecting modules. Metadata collecting module performs the task of collecting metadata. Some information may be retrieved directly from the APK files, such as application names, version, size. Then APK files will be unzipped to analyze meta info folders, and finally APK tunes will be used to disassemble Android manifest.xml files and classic.txt to decompose those files to text form. Some data contains the information about these wrapper, libraries, accessor, request permission, etc. After that, the metadata analysis modules will convert the collected data into feature vectors. I set values for each feature, and with the number information it is kept in the vector with other features. I have defined some tokens and set the values may be 0 or 1. Training and detecting modules will read the trained datasets from text file and then use a model that fits the datasets. After so that the system uses a model to predict for new data. The results may be on or minus on. It means on is malware and minus on the BI application. In the experiment, I split into two test cases. The test case one is to scan detect Android malware, and test case two is scan BI applications. This table shows the development for the experiment.
Yeah, 200 or 200 samples malicious.
100 samples.
200 samples. Training data. What kind of sample data?
Malicious. Training only for malicious. And I scan 101 malware and 239 BI applications. The test case one is 101 malware scanning, and test case two is BI application scanning. This is the classification results for two test cases. Each side 101 malware, the system classified 74 malware, and in BI there is 42 malware. That's a misunderstanding. This is the time consumption. It's an experiment for 239 samples with a size of 303 megabytes. Here is the evaluations. The total accuracy of the system is 79.7%. And the paper shows two positive, two negative, false positive, and false negative rates. This is the performance evaluations. Time for each megabyte is nearly 2 seconds, and for each app is nearly 3 seconds. According to these results, the system is faster than the malware detection using collaborative schemes in a network. Let's propose to implement a system which can scan and detect malicious application by analyzing enterprise application metadata. The result shows that metadata is useful for malware detection and more easily examine large number of Android applications. In the future, I will do some work focused on improving the performance of the system and accuracy, such as choosing features for better carefully improving metadata collecting modules and unpacking applications. Here are the references. Thank you for listening.
じゃあ、とりあえずいろいろ聞きたいんですが、このナーさんが作っていた日本語でいいよね。この作ってくれたシステムが僕のMacOS アンドロイド上ではどうかな。
そうですね。パソコンで。
で、まずそれを確認して、最後にコンクルージョンのところで、リザルトとして成功って書いてあるけど、何を見てるか教えてほしい。
成功は、
アキュラシーの 80% で、
秒から5秒ぐらい。そうです。僕のシステムは3秒ぐらい。トレーニングは、サンプルのデータを読んで、モデルを作ります。
SVM でトレーニングしてる。
そうです。
で、300メガバイトで、メタデータだから、このくらい入る学習になってる。
そうです。
で、そのイデーションの比較したものは、その辺に全部要数が全部自分の方がそれも結果のリテイクのところだけが上回っている。その先行研究と比較したときに、どの部分が上回っている。トータルだけが上回っている。学習時間とかは向こうの方が早い。
全体的に早く。
全部が早い。
トータル時間。
精度は上げなくてもいい感じ。
そうですね。早くは一番。
例えば、その先行研究と比べるなら、この、先行研究が4秒ぐらいだって4秒ぐらいだったら、学習データをもうちょっと増やしても、基本的にはそんなに、トータルで学習時間は増えないですね。なので、それをやっても結局、最終的には、精度はそんなに上がりすぎないとか、そういう理由が、そうなんです。学習例をたくさん増やして、基本的に要数がそんなに増えないけど、精度は上がります。そういうのがあります。せっかくだからそれをしっかりやってみて、そんなに学習例が多くなくても、このまま精度が同じなのか、それとももっと学習例を増やしても、トータルの時間としてはそんなに変わらないけど、精度がもっと上がるとか、そういったものは買った方がいいんじゃないかなと思いました。
So what is the definition? How did you define the malware on Android?
So malware is defined by other samples.
How did you get that? And what is the difference between malware and benign in this research? Will that affect the result? So
There are some.
You got 100 malware samples.
Yes.
You tested with about 300 elements of software. So I wonder why you can train only by malware. You don't have to have a benign software.
Because I use on-class supported machines because only two types of application, that is malware and benign. So I use this easy mix only from malware software.
If you have both malware and benign software, that may make better results. Why you decided to have just one training data by malware? So you have the answer. You should have the answer for that kind of question. So
create a boundary for the feature vector from the samples. And when applied for the new data, just what is inside the boundaries will be classified as malware, and outside is BI.
So what part of metadata was has a significant role contribution to the final result?
The metadata is certificates, information, and permission.
But I think the metadata is a set of parameters. So the some parameter should have more impact to the result, and the others are less impact. So I want you to tell that kind of things, and also I want you to mention those kind of analysis. You know, it can be just your estimation is okay, but you should have some assumption. This method work because I think this is how this works. In my feelings, the 100 samples is kind of little compared to the data half of evaluations with the data data. But I don't know why that's fast. Why is that? Why you only use only 100 samples?
Actually, I already had about 300 samples, and I divide to test and sample.
Why you don't want to just half? We have 300 and 150.
I don't know.
You don't know. But you have that. You have some easy.
このところの少し見ましたんですけど、サンプル2章のところに、コードベクターのところがあって、C ベクター、C サックベクターマシンとか、V サックベクターマシンとかってあるけど、これの違いは分か